6.2 Trigonometric Equations. So solve a trigonometric equation by linear methods. So how do we know we have a linear model or a linear function or a line? Because you only have the power of 1. There's no exponents. It's just, there's no squares, there's no cubes, there's none of that. So because sine theta is to the first power, we use the same methods as we would a linear equation. Meaning solve like you're just solving for x. Remember, x, theta, all that, it just means a variable. So we have our function 2 sine theta plus 1 equals 0. So I need to get theta by itself. So I'm going to subtract 1 to both sides. So we have 2 sine theta equals negative 1. Let's divide by 2. So sine theta equals negative 1/2. Cool. Now we have what sine theta equals 1/2 is. We have that. Now let's find theta. So to find values of theta that satisfy sine theta equals negative 1/2, we observe that theta is in quadrant 3 or quadrant 4 because sine is negative. So let's use the unit circle. So using our unit circle, sine theta equals negative 1/2 in both quadrants, 3 and quadrant 4. If you look at it, we have 210 and 330. Both of those give us sine of negative 1/2. The reason why we use degrees is because they ask in degree mode. So our solution set is 210 degrees, 330 degrees. All right, example 2. So we're going to use the same example, but for all solutions. Do you notice the difference? It just says over the interval 0 to 360. This one is all solutions, meaning, you know how we have coterminal angles? So we have like those, and then we have angles that like can go for like 1400 degrees. So how can I find the answer if I rotate a bunch of times? Alright, so to find all solutions, we add an integer, so n, multiples. So we add integer multiples to the period of the sine function. So the period of the sine function is 360 to each solution found in example 1. So in example 1, we found our first answer of 210. So we're going to add that to the integer of our period. So our period is 360 and n. So n is how many times are you going around, how many periods are you making. Then we're going to do the same exact thing with our other answer. We have 330 degrees. Then we're going to add that to our period of sine, so 360 and n. N is how many times are you passing through the period. You do that every time you want to find all solutions. So once you find the solution or the solutions, you can use the period to find every single solution. So if I went around 100 times, I can still find theta by plugging in 100 as n. Oh, something I forgot to say, you have to stipulate where n is any integer. Meaning n can be anything. My bad. Alright, solving a trigonometric function, zero factor property. So we have sine theta tangent theta equals sine theta over the interval 0 to 360 degrees. Alright, factor property, that's when the equation equals 0. You know, every time how you say you set the equation equal to 0, that's called the zero factor property. So let's do that here. In order to do that, I'm going to subtract sine over. So we have sine theta times tangent theta minus sine theta equals 0. Now they both have sine in common, so let's take it out. So if we take out a sine, we're left out with tangent theta minus 1 equals 0. So you see how it's factored? Because we factored it. Now we're going to set each equal to 0. So we have sine theta equals 0 and tangent theta minus 1 equals 0. So use your unit circle. Sine equals 0 at 0 degrees and 180 degrees. Here we have to solve for tangent, so we add 1. We have tangent theta equals 1. So remember, pay attention to your quadrants. So since it's positive, we're going to be looking in the positive quadrants of tangent. So quadrant 1, and wait for you to think about it. You got it? Quadrant 3. So in those quadrants, tangent is positive 1 when it's 45 degrees and 225 degrees. So our solution set is 0 degrees, 45 degrees, 180, and 225. Order does not matter, but it's liked. You see how I forced us to solve it and make it equal to 0? You should always try to do that. Trying to solve the equation by dividing each side by sine would only lead to tangent theta equals 1. We'd be missing part of our answers. So that's why we equaled it to 0. So if you have multiple functions going on and some are the same, equal it to 0, then factor it out. Alright, let's solve tangent squared x plus tangent x minus 2 equals 0 over the period of 0 to 2 pi. So, do you notice that we have a quadratic? We have a quadratic because of that too. So the only way we really know how to solve quadratics is by factoring. So let's factor this. So different signs because that's a negative. So 2 times 1 equals 1. So we have tangent x minus 1, tangent x plus 1 equals 0. So we have tangent x minus 1 equals 0, tangent x plus 1 equals 0. Let's keep solving. We have tangent x equals 1, tangent x equals negative 1. So let's figure out where these values exist. Tangent x equals 1. That is at pi over 4 and 5 pi over 4. Now, tangent x equals negative 1, our values on the unit circle don't support that. So we need to do something special there. I'm going to switch screens real quick because I don't feel like writing a paragraph. wish I could do elevator music for you, but I can't. Alright, here we are. So, to solve tangent x equals -2 over the given interval, we must use a calculator, because that value on the unit circle doesn't support it. So, in radian mode, because we're working with radians, we do the inverse of tangent 2, and that equals approximately -1.10714887. That's in quadrant 4. Since we want solutions over the interval of 0 to 2 pi, we must add pi to -1.101 or 0.71487, and then add 2 pi. So we add pi to get it into the quadrants that we need, 1 and 3. So we need to get this into the proper quadrant, so we add pi, and then we need to get our other value, or the same value, add it to 2 pi, and those are our answers. We have the exact answers of pi over 4, 5 pi over 4, and 2.0344, and 5.1760. You're going to do this when your tangent is not supported with the unit circle. Alright, go ahead and take time to pause that and write all that. I just didn't want to write it all. Alright, let's go back to our notes. Alright, example 5. Find all solutions, so that's the one where we have to have that n thingy, of cotangent x times cotangent x plus 3, and let's write the solution set. Oh, I forgot a part. Sorry, this is supposed to read cotangent x times cotangent x plus 3 equals 1. Sorry, that's missing. It's missing that equals 1 part. Alright, so we have parentheses. Let's do what we usually do, distribute. So when we do, we have cotangent squared x plus 3 cotangent x equals 1. You probably guessed it, we're going to minus the 1 over. So we have cotangent squared x plus 3 cotangent x minus 1 equals 0. The reason why we equal it to 0 is because cotangent is squared. Now, we cannot factor this because two numbers that multiply to 1 do not subtract to 3. So since we cannot factor, we need to use the quadratic formula. Yeah, pulling everything from algebra into this. So we have, remember, we have A, B, C. So B is 3, so we have -3 plus or minus 3 squared, minus 4 times A, which is 1, times C, which is -1. Your values are always the number in front of the function, and then 2 times A, which is 1. Use your calculator. Your calculator can do all of this. I'll still show you step by step though. So we have -3 plus or minus 9 plus 4, which is 13, all over 2. So we technically have two values. We have x equals -3 plus square root of 13 over 2. And then we have x equals -3 minus the square root of 13 over 2. So when we do -3 plus square root of 13 over 2, we get cotangent x is approximately 0.3027756377, and when we plug in -3 minus 13 square root of 13 over 2, we get cotangent x is approximately -3.30277563.8. We need to take the inverse of those because we need actual values. So we have x equals the inverse of tangent. We're going to plug all of this in. So plug that into there, and we get x is approximately 1.276795.025. Same thing for here. We get x equals inverse of tangent. We're going to plug all of this into here, and we get x is approximately negative 0.294001318. But do you notice that this is negative? My bad. That is negative. So since it's negative, we need to add pi. So when we add pi, we get x is approximately 2.847591.352. So our solution set there's our answer. Why do we add pi to have n pi? Because remember, period of tangent is pi. Alright, example 6. Let's solve a trigonometric equation by squaring. So we have tangent x plus square root of 3 equals secant x over the interval 0 to 2 pi. So we need to write this as a single trig function. So you see how we have secant? We can't have multiple types of functions because we can't get rid of it. So we need to square it. And you see when we square it, we're actually going to get something out of it. So let's square both sides. So when we do, we have tangent squared x plus 2 square root of 3, tangent x plus 3, so FOIL, and that equals secant squared x. So the reason why we did that, because secant squared x equals 1 plus tangent squared x. So you can see how we can replace it to get rid of the secant. Alright, because it's a quadratic, we're going to equal everything to 0. So I'm going to subtract 1 over. And then I'm going to subtract tangent squared x over. So we are now left with 2 square root of 3 tangent x plus 2 equals 0. Alrighty. Let's move that 2 over. I don't know why I did that. Well, I guess it doesn't matter. We can factor it out. Let's factor it out. They have that in common, so let's take it out. We have square root of 3 tangent x plus 1 equals 0. We've set each of these equal to 0. So we have 2 equals 0. That doesn't exist. And then we have square root of 3 tangent x plus 1 equals 0. So we have square root of 3 tangent x equals negative 1. We're going to divide by tangent x. So our solution is, we're getting there. Our tangent x equals square root of 3 over 3. So those values, negative square root of 3 over 3, can be found at (5 pi over 6) and 11 pi over 6. Do you remember that when you factor quadratics and you get solutions that you're supposed to check your answer with radicals? So you see how we have a radical and a quadratic? We have to check our answer. So we have to check 5 pi over 6 and 11 pi over 6. So we have to plug it back into the original equation. All right, let's do that. So our original equation, we have tangent x, which is 5 pi over 6, plus square root of 3 equals secant x, which is 5 pi over 6. Use your calculator. So tangent 5 pi over 6 plus the square root of 3 is 1.154700538. And secant 5 pi over 6 is negative 1.154700538. So that does not equal. That does not equal, meaning 5 pi over 6 is not a solution. It's called extraneous solution. Now we have to check our other one. Use your calculator. We're doing the same thing except with 11 pi over 6. So we have tangent 11 pi over 6 plus square root of 3 equals secant 11 pi over 6. And we get our values of 1.154700538, and it does equal secant 11 pi over 6. Radian mode. So our only answer is 11 pi over 6. Alright, helping solving. Where do we start? Decide whether the equation is linear or quadratic. If only one trigonometric function is present, first solve the equation for that function. If more than one trigonometric function is present, rearrange the equation so that one side equals 0, then try to factor and set each factor equal to 0 to solve. If the equation in quadratic form but not factorable, use the quadratic formula. Make sure you check your solutions. Try using identities to change the form of the equation. It may be helpful to square each side of the equation first. In this case, check for extraneous solutions. Alright, this next example, I kind of just have to walk you through it because it's a lot of explaining with your calculator, so I'm going to have to switch to my other screen. Alright, example 7. A basic component of music is a pure tone. The graph below models the sinusoidal pressure y equals p in pounds per square foot of a foot from a pure tone at time x and t seconds. The frequency of a pure tone is often measured in hertz. 1 hertz is equal to 1 cycle per second and is abbreviated Hz. What is the frequency f in hertz of the pure tone shown in the graph? So from the figure, we see 6 cycles. So 1, 2, 3, 4, 5, 6. So if we have 6 cycles and 0.04 seconds, that's 6 divided by 0.04, that's 150 cycles per second. The pure tone frequency is 150 hertz. So part B, the time for the tone to produce one complete cycle is called the period. Approximate the period t in seconds of the pure tone. So 6 periods cover a time of 0.04 seconds. That means one period is 0.04 over 6, or 1 over 500, or 1 over 150, or 0.006 seconds. Do you notice that we just flipped this, and then we use our calculator. All right, part C, an equation for the graph is y equals 0.004 sine 300 pi x. Use a calculator to estimate all solutions to the equation that make y equals 0.004 over the interval of 0 to 0.02. So press y equals, input your function into y1, and so 0.004 sine 300 pi x, and then in y2 we do 0.004, and that is because it told us right here. Press window, your x minimum is 0, your x max is 0.02, your y minimum is 0.006, negative, and your y max is positive 0.006. And we got the 0.006 from here. You see how it's underlined right here. And then we got the negative 0 to positive 0.02 from here. Okay. After that, you press second trace, 5 intersect. For the first curve, you go to the left intersection and see the image. Press enter. Second curve, just press enter, make sure the dotted tracer is on y equals 0.004, and we get those values. So I did the second curve, and I did all the steps here, so you know what it looks like. So first, you have to do it to all curves. So all intersections, you have to do this 3 times. So if you go to any of them, it's the same thing for every single little bump. It's the same, every intersection is the same process. So if you wanted to do the left one, first curve, the little dotted thing will be right here. And you press enter, and then your y2, your second curve, just make sure it's on the red line right here, somewhere right here for the first one. Press enter twice, and then you get your values. Okay, so I did this for the second and the third. So see the images. If you need help, just let me know. And we have those values of 0.0017, 0.0083, and 0.015.